So here we are at the end of the first unit. What we want to do is start looking at some applications. We're going to start putting the business into business calculus. So we've looked at limits, and we use that to build up this idea of what continuity means, and then also to talk about the derivative. What we're going to do is look at our first application of the derivative in a business context. We've maybe seen some other applications with slope and things like that, but here we go. So these are the three things that we're going to talk about. We're going to talk through just a basic setup with some definitions of things that we should know, and then we'll apply the derivative. We'll look at some other calculations, and then we'll try and figure out how to interpret all that stuff. So here we go. Let's start with our basic setup and some early definitions. These are some things that we'll just need to know. We're going to talk about cost, revenue, and profit. When we talk about C of X, that's going to be a cost function. That's telling us it's the total cost of producing X number of items. So if I evaluate this function at 500, this is going to be the cost of producing all 500 items, whatever we're doing. R of X is the same thing, but for revenue. So it's the money that we're bringing in from selling things. And P of X, the capital P of X, is the profit that we'll make. The amount of money that we'll be able to take home after all of our expenses. Typically, we'll be given the cost function, C of X, and then something called this price-demand equation. So let's just take a look at it. Right now, I'm just going to say it's an equation that's linking P, which is going to be a price in terms of dollars, and X, a demand. If you've taken an econ class, then you know that price is linked to supply and demand. We don't just have like a fixed price, like, oh, I'll sell this thing for, $15. That price is going to fluctuate if we produce too many things and we flood the market with some sort of an item. If we have a really high quantity, then the demand might, or if the demand stays the same, then the supply might be too high, and that could tank the price. Or similarly, if the demand of something gets really, really high and the supply stays the same, then the price might go up. So that's something that we're going to use. Notice we're using X for demand and for the number of things that we're producing and selling. We're going to assume that we know exactly what the market demand is, and we are going to produce and sell exactly that number of things. That's kind of a big assumption that doesn't really happen in real life, but we usually will try and use our best guess at it. Here, we're going to assume that we're doing exactly the same thing, so we're just going to call it X in both cases. So again, typically we're given C of X in our price-demand equation. If your price-demand equation isn't written like P equals something, what I mean for this is like P equals blah, 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 with maybe an X in here, blah, 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 then solve it for P. Make it look like this. The reason we want to do that is so that we can use this little equation to find revenue. Revenue is really price times quantity. It's the number of things that we sell, which is X, multiplied by the price at which we sell those things for. That's going to tell us how much money we're making. Profit is obviously going to be revenue minus our cost. So it's our R of X function minus C of X. Notice that we can put these things in parentheses to make sure that we're subtracting things correctly, but I'll show you what that means a little bit later on. These are two things that you'll just have to know. We're going to refer back to, and from pretty much here on out, I'm going to assume that whenever we're talking about stuff, you guys just know revenue is price times quantity, profit is revenue minus cost. So I might ask you about something with the profit function where I only give you cost and your price-demand equation. You would have to build the revenue function first, then go ahead and find your profit by doing this subtraction. So again, that shouldn't be too bad as long as we just keep that in mind. All right, let's talk about how we apply the derivative here. So the main thing that we're going to do, we've been talking about marginal analysis. That's what this section is. We're going to talk about what marginal cost, marginal revenue, and marginal profit is. If you've taken an economics class, you might know a little bit about what marginal means. Marginal is, normally we think of it, if we're talking about marginal cost, we'd think of it as like an added cost, or maybe a change in cost. Oh, my handwriting is really messy today. Notice that if we're talking about a change, a rate of change, that's going to make us think derivative. So whenever we see marginal something, you're going to say derivative of something. So marginal cost is really the derivative of cost, C prime of X. And we'll use our regular derivative rules to find that. And that's going to be the marginal cost of producing X number of items. Same thing for revenue. If we are looking at marginal revenue, we're just going to find the derivative of revenue. If you're asked to find the marginal profit, you'll be looking for the derivative of profit. So the thing that I would stress is that marginal means derivative. If you're asked to find the marginal something, you find the derivative of that thing. So marginal cost is the derivative of cost. Marginal revenue is the derivative of revenue. Marginal profit is the derivative of profit. Marginal anything else is the derivative of whatever else comes after it. Average, this is another one that we'll talk about. This one's pretty easy. Average is normally a total divided by a quantity. Normally we add things up to find that total. Here, our C of X function, R of X, and P of X, those are total cost, revenue, and profit. So if we want to find average cost, which we'll represent using this bar here, we'll call this C bar. That represents average. Maybe you've seen that notation before, maybe not. But what that's going to be is just our total cost divided by the number of items. So if we want to find an average cost, take the total number of costs that we have to spend to produce all those items, divided by the number of items we've produced, and that should give you an average cost per item. We can do the same thing with revenue and the same thing with profit. Again, nothing really groundbreaking here. We're just trying to get some of these definitions, terminology, all that kind of stuff squared away. Interpretation. The derivative is a rate of change. When we're talking about marginal cost, revenue, and profit, we're talking about a rate of change of the cost, a rate of change of the revenue, and a rate of change of the profit. This here is a little bit confusing to read, I think. So I just want to kind of explain what this means. First off, if you haven't seen this symbol before, this little squiggly equals sign, this is approximately, meaning it's not exactly equal to, but it gives a good approximation of. Marginal cost, it's an added cost due to producing the next item, or we could say one more item. So for instance, if we were looking at C prime of 50, what we're doing is we're looking at the increase in cost due to going from 50 items to 51 items produced. And a lot of times we'll be given some sort of a time unit, maybe this will be in weekly production or something like that. So we can say if we're right now producing 50 items a week and we want to see what the added costs will be if we add one more item to our production, we can look at the derivative at 50. So that's why we've got this x plus 1 here. Basically what we're doing is saying that this derivative is going to make a prediction of what the increase in cost is going to be. Now, we could expect that the cost is going to increase. We would hope that the revenue would increase as well. But what was kind of interesting is that sometimes our profit will be increasing or decreasing. So depending on the number that we get when we evaluate our profit function, here, if we're looking at P prime of 50, we're just going to say it's the change in profit. Could be positive or negative, due to going from 50 items to 51 items produced. So this is going to try and get an idea of what the impact is going to be of making these decisions. Should we increase our production or should we leave it where it's at? All right, let's take a look at an example and we'll see how this works. I think one example is pretty good. There's lots to do in the homework and stuff like that here, so jump into those practice problems and get a feel for it. But this is an example I think is in the textbook. Maybe I've changed some stuff. I don't exactly remember. But anyways, we've got a company that's producing LED light bulbs, and they do some market research. They dig into their financials, and they get a cost function and this price-demand equation. You'll notice that I've already solved the price-demand equation for P. If it's not written in terms of P, write it in terms of P. Just do some algebra to get it written like that. I'm going to give it to you every time this way. We're going to do three things. We're going to first find the domain of the price-demand equation. This is an interval of x values. what we'll notice is that this domain is going to be the same as the domain for our cost, revenue, and profit functions. Basically, we're going to be saying how many items are we even able to produce? What's a reasonable range of items to produce? And we'll answer that question. Then we're going to find the marginal profit. To do that, we'll have to find the profit function because we're not given that. This lowercase p here is not profit. This is price. We'll have to find capital P. So we'll have to do that, and then we'll evaluate it at 5,000 and try and figure out what the heck that means. We'll do the same thing for the average profit function. So first things first, let's deal with this. Oh, I should probably write down the price-demand equation. Our price-demand equation is 10 minus 0.001x. So P equals 10 minus 0.001x. Cool. All right, let's go ahead and answer these questions. We're always going to ask two questions to find the domain. We're trying to find some x values, so we're trying to figure out the production here, right? So we want to find out what's the smallest number of items that we can produce. Is 10 the lowest number of items we can produce? No, we can produce lower than that. What about like 1? Can we produce less than 1 item? We don't really deal with fractions of items, but we'll use that in our interval of values. We'll assume that we can put in decimals. So what we'll say is that x here has to be greater than or equal to 0. At worst, we're going to produce nothing. That's always going to be the case. The least number of things that we can produce is always going to be nothing. The harder question is what's the most we can produce? But we can kind of frame this in a bit of a different way. We know that price and production, or price and demand, are linked. And so if we're trying to figure out what's the most number of things that we can produce or sell, we're going to really ask, what is the lowest price? It's pretty obvious that P equals 0 is the lowest price. So if we want to figure out what the most production that we can do is, we're essentially going to say, what happens if we put 0 in for price? How many things can we just give away for free? And let's solve this equation. Super easy equation to solve. Add this 0.001x to both sides. Divide by 0.001, and we've got that our most production is 10,000. So what we've got here is that the least is 0, the most, maybe I'll say this, it has to be less than or equal to 10,000. So we can come up with an interval now like this. This is going to be really helpful for us if we want to start visualizing things later on when we want a domain on some of these cost, revenue, profit functions. We'll do this type of thing. We're always going to ask these kinds of questions, these two questions. Now, in a lot of cases, you'll notice that you'll just be given this interval. Maybe right off at the beginning, we'll say something like this. And so you won't actually have to find it. I just wanted to show you how to do that. We'll try and remind ourselves about that if we ever need it, but that's how we'll find this interval, by asking what the least number of things that we can produce is. X has got to be greater than or equal to 0, and what the most things that we can produce is, which is by finding the lowest price. So that's how we can solve that little bit. Anyways, let's get into the actual calculus. What we want to do is find the marginal profit function. So to do that, we're going to need to find revenue first. Revenue is X times P. So this is going to be X times, what was P? 10 minus 0.001X. There's a decimal right there. There we go. So we've got 10x minus 0.001 x squared. This is our revenue function. So if we want to find profit, what I'm going to do, maybe I'll call revenue blue and I'll call cost red. We're going to take our revenue function. That's 10x minus 0.001 x squared. And we're going to subtract our cost function, which was 7,000 plus 2x. Now I've put parentheses around here because if you don't, what a lot of people will end up doing is they'll say like, okay, if we subtract 1,000, then add 2x if they forget these parentheses. Let me show you what that would look like. I'll get rid of these things just so you can see. So they'll forget that they're actually subtracting 2x, so they would say like 12x instead of 8. Don't forget that we're subtracting the whole cost function. So our profit function, is going to be, I'll write it in a nice order, negative 0.001x squared. Our 10x minus 2x becomes 8x. And then we've got minus 7,000. Cool. So this is profit. So if we want to find the marginal profit, what we can do is just take a derivative of this thing. So for marginal profit, we're going to look at the derivative. I'll give you a second to find this. This shouldn't be difficult because we're just using power rules and stuff like that. So take a second, pause the video, find this, make sure you're good. Okay. If you haven't done it, go back and do it. But this is what you should end up with. Negative 0.002x plus 8. Now, if we want to evaluate this at 5,000, we're going to say, all right, what's p prime of 5,000? Meaning we're looking at negative 0.002 times 5,000 plus 8. So negative 0.002 times 5,000, is that going to be 10? Negative 10? Let me double check that real quick. I've got a calculator off to the side. Negative 0.002 times 5,000. Yeah, okay, I'm right. Negative 10 plus 8, negative 2. All right, so if we want to interpret that, this is a change, because it's a derivative, it's a change in profit. Meaning right now, if we're producing 5,000 units, I don't know, per week or per month or whatever our time frame is on this thing, if we change that, if we increase it by 1 unit, we're going to actually start losing money. Now, our profit won't be negative. We're just going to decrease our profits by $2. So what we'll really notice is that this wouldn't be a very good decision. We shouldn't increase our production because our profit is going to go down by $2 because this here, again, that is a change in profit. So our real assessment of this would be not to do anything. Don't increase our production here. Don't change it at all because we'll actually start decreasing our profit a bit. All right, let's go ahead and do the average profit. I should have put a spot here for the profit function. Let me go back and see. It's this negative 0.001x squared plus 8x plus 7,000, I think. Or sorry, minus 7,000. Duh. Let me fix that. All right, cool. What we want to do is find average profit. Average profit is going to be profit over our quantity x. So I'm going to say negative 0.001 x squared plus 8x minus 7,000 all over x. Notice we can split this fraction up and then reduce everything. So we're really going to be left with negative 0.001x plus 8 minus 7,000 over x. So if we want to find the average profit evaluated at 5,000, we're looking at negative 0.001, oops, not x anymore, times 5,000 plus 8 minus 7,000 over 5,000. So this is going to be negative 5 plus 8 minus 7/5. Negative 5 plus 8 is going to be 3 minus 7/5. I'm looking at 15/5 minus 7/5. So that's going to be 8/5. Or we could say 1.6, I believe. Double check that. But this is what we've got here. What this is that it's going to give us about an average profit of $160 per unit when we're producing 5,000 units. So again, this is an average profit that we can say per unit. Each unit approximately is bringing in $1.60 in profit. And I don't even remember what we were looking at here. Oh yeah, LED light bulbs. So whether these are packs of light bulbs or whatever, we're making in profit about $1.60 per package of light bulbs or light bulb, whatever we're looking at, when we're producing and selling 5,000 of these things. Cool. All right, couple things to think about. We can use the domain of our function to graph a nice little setup here pretty easily. What we'll find in a lot of cases is things like our revenue function looking something like this, and a cost function looking something like this. So maybe I'll label that as cost, and I should label this one as revenue. What you'll notice is that the profit is the difference in between them. And so you might notice that over in here, revenue is higher than cost. And so this is when they're making profit. Outside here, see how revenue is below cost? This is when they were operating at a loss. We could also notice that we've got these 2 points here, these intersection points. We call these break-even points. You can find these intersection points graphically. What I would do is set your window up using the interval that we found. In our case, I think it was like between 0 and 10,000. Let me just double check. Where was it? Yeah, right here in this box, 0 and 10,000. You can make that your window for these things. So maybe make your X min 0 and your X max 10,000. And then if you're looking at your graphing calculator, go into the zoom menu and find zoom fit. That'll give you a picture that looks an awful lot like this. So you can use just the nice graphical interpretation of all that to find these intersection points, those break-even points, all that kind of stuff. You can see a nice picture of what's going on. The other thing to think about is, what about marginal average profit? What do we think about this? Marginal is derivative of, so this is the derivative of the average profit. And we could try and interpret this by thinking that this is a rate of change of the average profit when we change X by 1. So if we increase our production, our average profit will be changing a little bit as well. I'll let you play around with that, but these are some things to just kind of keep in mind and notice. That's everything we've really got for application stuff. Notice there's nothing really new in the calculus. You're still doing all of your differentiation the same way. You don't have to use that limit definition of the derivative anymore because we've got all these nice properties and shortcuts figured out. But jump into this stuff. Hopefully you find that it's not too much of a leap from what we're doing here. You'll notice that in a lot of these, the setups are going to end up being pretty similar. And we want to make sure that we're settled into all of this because we're going to use this same setup for a lot of different applications throughout the summer or throughout the semester. So jump into this. Make sure you've got this all figured out. But there's not a lot going on here. Hopefully that works out pretty well.